Hello, friends. This is a video on the energy of processes. When you have a nuclear process that's similar to a chemical process, you can have either endothermic or exothermic reactions, meaning energy is either released, boom, or energy needs to be inputted to form new nuclei. What's different about this in chemistry is that we're dealing with mass on its fundamental level, mass as energy. So mass can be converted to energy, and energy can be converted to mass, where mass is determined by the mass of the nucleons plus the binding energy. So a reminder here that for a single nucleus made of protons and neutrons, the mass is the sum of its parts plus the binding energy, where the binding energy is negative due to the strong force and positive due to the electric repulsion of protons. Which one wins? Well, the negative strong force wins, of course, but the positive aspect is important for bigger nuclei and is incorporated in this value when we calculate the mass of certain nuclei. Both are important. Ultimately, both are incorporated in this single term, though. You don't normally have to do them separately. It's just this is the binding energy. It's full stop, but just know that the binding energy contains both of these. So it's simple. This, though, will be important when we get to bigger nuclei, and I say, wait, why does the mass stop getting smaller? Well, because the positive repulsion prevents that, and it actually ends up pushing the nucleus apart. It limits how big a nucleus can get. Those protons just don't want to be together. For a process, for instance, this process here, you have reactants that become products. And energy is either inputted or outputted. Input means endothermic, output means exothermic. You want to solve for the mass difference, products minus reactants. Think of it as final minus initial. Final minus initial. And energy, the energy inputted or outputted, is delta MC squared. So what we're doing is we're taking all this background and we're summing it up into pretty much one simple equation, E equals delta MC squared. So delta M, final minus initial, I'll write it more formally here, is M products minus M reactants, right side minus left side. And the energy, inputted or outputted, is delta M times the speed of light squared. Don't forget that the speed of light squared is 9 times 10 to the 16. Always. That one's easy. Now, if delta M is negative, take a moment to think about this. If delta M is negative, which one's bigger? The reactance is bigger, which means we lost energy. That makes sense. That's what the negative means. We lost energy, or the nuclei lost energy due to a binding energy. Boom, clap, that energy got released out. That's exothermic. If delta M is positive, that means the nuclei grew, or the nuclei became less bound. And that means energy had to be inputted to make that happen. So you can think of outputted as more bound nuclei. And energy inputted as less bound nuclei. And I'm drawing that process, the visual of that on the next page. I hope that makes sense. This is quotes less bound nuclei. So we have this example of deuterium plus tritium turning into helium-4 plus a neutron. Here are the numbers. Pause the video and make sure these numbers make sense. You'll notice that deuterium plus a neutron gives you tritium, but it's a little less because it's more bound. Remember, more nucleons, and I'll write this on the next slide actually, more nucleons. What is a nucleon? It's just a proton or a neutron. That's it. that which makes up a nucleus, right? More nucleons means more binding energy, which means less mass. Right? A larger clap when it forms. There's an asterisk here that I'm going to write down in a second, but the whole point is that when you form helium-4, look, deuterium plus tritium coming together. This is what it looks like. They come together, boom, strong force activates at about 2 femtometers, and boom, it literally like pulls them together. You get a smash, and that smash, right? You think of potential energy converting to, think about it slowly in slow motion, potential energy converting to kinetic energy, like two cars colliding, and then they smash into each other and stop. Well, where'd that energy go? It went into heat. It went into light. Heat meaning what? What is heat? Heat is vibration. Heat is kinetic energy outputted into the environment, right? So say they hit each other and vibrate, and that makes the next molecules vibrate. It heats up the system. It heats up the star or the reactor or the air or the fluid or the plasma, whatever is around it. And that neutron's also going to have some energy. It flies off. It engages with the environment, manifesting as temperature, as higher heat being put into the environment. Rewind the video, and I said those words. I hope that visual makes sense. It's a slow motion collision, potential energy to kinetic energy, and the kinetic energy therefore manifests as light or vibration, which then gets transferred into the environment. The point is it's lost. Now that heat can be used, say it gets hotter, you can gather that heat and heat up some water, boil it, that steam will turn a turbine, which turns a generator, you got electricity. That's how nuclear reactors work. That's how that's how the sun works. The sun doesn't boil water, but the sun gets hot, and because it's hot, it shines, and therefore we live. So this is the process. Boom. More nucleons means more binding energy, which means less mass, which means energy is released into the environment. A little cleaner. All right. Now, I wrote like a larger clap when it forms. Now, the asterisk is that too many protons, as we're going to see, and we're not going to study this yet, but we're going to get there eventually. Too many protons has a positive repulsive binding energy of repulsion. It wouldn't be called a binding energy. It's actually called a repulsion energy, right? A positive energy of repulsion, which means it reduces the binding energy, reduces the magnitude of binding energy of the negative, otherwise negative binding energy. The point is the strong force is trying to pull things together. The electric force is trying to pull things apart. And the strong force wins, but if you have too many protons, the electric force actually starts to matter a lot. And so more nucleons actually reaches a point around iron where you start to actually get less binding energy, right? Less binding energy, more negative, I should be clear here. More negative binding energy. With the asterisk of too many protons, actually, you result in less negative binding energy. Binding energy is always negative, but it reduces the magnitude of it if you have too many protons. And that's going to become important. That leads to something called fission instead of fusion. And that's a really important cusp to know. So our stars stop working. And so our fission reactors start working on our human planet inventions. So in terms of an example, this example is one that humans are trying to recreate on the Earth. Some have actually done it successfully to small increments of greater and greater degree, and I'll overview what that is later. You might hear it in the news. But deuterium-tritium fusion is the easiest to do on Earth, and it produces a very large amount of energy output per what it takes to put into it. And we can look at those numbers together, which I think is kind of fun. Now, what I'm doing is I'm looking up the answer, which I left blank down here. Got it. If you take deuterium and tritium, here are the numbers, and you take helium-4 and a neutron, you see that they don't add up, meaning the masses on one side are bigger. You'll notice that masses on the reactant side are bigger than the masses on the product side. So if you subtract final minus initial, you get a negative value. And this is what you should get. If you guys want to take a moment, add up D plus T, right? You're going to see it's more than adding up helium-4 plus a neutron by this amount. If you just plug it into this formula, you're going to get this. You multiply by C squared, you're going to get 2.7272 times 10 to the negative 12 joules. So released per clap. So if you get deuterium and tritium to actually fuse into helium-4, you get a neutron. That's actually an issue. Those extra neutrons are a thing in nuclear reactors we're going to see. And you get energy. You get heat. It heats up the system. I don't know if any gamma rays are released. They probably are, but I'll have to check on that. But definitely heat. You get vibration, energy released into the environment. It heats it up. You might have heard of like net positive reactions. The point is you want the energy out to be more than the energy it took to get these things to fuse, because you actually still need some energy input to get these things moving in the first place. And we'll talk about what that is. Either way, I don't know if you guys noticed, but this negative 12 is bigger than the negative 13s that we're seeing for nuclei. So it's actually an order of magnitude high. It's high. I know it seems small. Of course it's small. It's a picojoule. But per nucleus, that's fairly large. So it's on the larger end, and obviously you're not dealing with single nuclei, you're dealing with a kilogram block of it, and that's trillions upon trillions, a trillion nuclei that you all want to fuse, and you get that. Anyway, there's the example of how you use this equation. This is for a single nucleus, and this is for a process. So this is the nuclear reaction. Products minus reactants. Hope that made sense. There's the picture. There's the concept flow chart. You guys are great. Boom. Have a great day.